All right, so let's say how the time domain analysis for this circuit will look like. It means we are trying to see the time domain response of this circuit. So this is, remember from the previous session, this is first order RC low pass filter, and the cutoff frequency, it was designed for the cutoff frequency of about 1 kilohertz. So for that we use the formula fc equal to 1 over 2 pi rc, and for the given value of 1 kilohertz we chose the value of capacitor to be zero point 0.1 microfarad, and then we computed from this formula the value of r to be about 1.59 kilo ohm. So you see here the value of C and value of R is there. And we have this voltage source for this RC circuit. So now we have to run the time domain analysis. We have to see its cutoff frequency of this circuit is about 1 kilohertz. So we have already seen the frequency response. Now we have to see how the time domain waveform or response will look like. So it means we apply a sine wave to this circuit with a particular frequency. So up to from 0 to FC, it will pass this signal at the output, and when we plot the response at the output, this signal with the frequency from 0 hertz to FC, which is 1 kilohertz design frequency, this circuit will offer a gain of 1, gain of unity to pass that signal we have seen in the frequency response, that is VO over VI, that is equal to 1 up to FC, and then it will start falling at the rate of minus 20 dB per decade, right? And this at frequency where it falls to the minus 3 dB point, from this is the 0 dB point, and we saw that to the point here where it falls from 0 dB to the minus 3 dB. So that point is called as cutoff point. So where the gain is minus 3 dB lower than the 0 dB or gain of 1, because 20 log 1 would be 0 decibel, all right? Or in terms of voltage, it has a 1 volt from 0 to, so 1 volt from 0 frequency up to FC, and thereafter it has the gain of gain constantly decreases, right? So at FC the gain is about 0.707 volt or minus 3 dB point. So this is minus 3 dB point in decibel, or 0.707 of the original gain, that is the one. So the circuit will not offer gain greater than 1. Maximum gain is 1. So let's see how we can do that. So to do so, what we need to do is, in the analysis, we have to select this voltage source, right click here, and we go to advanced. Then here we have to apply a sine wave source. So you see here are the parameters where DC voltage is set to be 0, amplitude let's say 100 millivolt, frequency, remember the frequency cutoff frequency is 1 kilohertz, so we can have any frequency up to 1 kilohertz. So let's say 250 hertz, delay 0, let's say theta 0, phase 0, and number of cycles we do it for, let's say about 10 cycles. Other parameters need not to be inserted because we are running the time domain analysis. We only need a sinusoid or voltage source. So we have that. Once that source is there, we can just offer to display it on the screen. And now we are running a time response or time domain analysis, unlike before. So what we do, we click simulate, We click edit simulation card. We select this transient analysis. You see it's automatically selected. So stop time. So this time x-axis will be time. So we can select, let's say 10 millisecond or 100 milliseconds. We have to start saving the data from 0 second itself onwards, and maximum time states about, let's say, 10 milliseconds. Rest parameters need not be inserted. So you see this command dot run 0 100 m. So it means it starts from 0 second to 100 milliseconds, and it starts saving the data from 0 seconds, and 10 milliseconds is the time states, maximum time state. So we click OK, and this command comes here. So once that is done, so let's click run. And now we have to actually plot the response. So we'll see how the response looks like. So we first remember this arrow here that offers us to plot the current through the devices and the components. So if I click here, it will plot the current through these voltage source. But if I go up and this pointer comes, so this means I'm plotting the node voltage of the voltage source. So here, so is the input voltage. See, we have given the 100 millivolt peak or 200 millivolt peak to peak sinusoidal wave. It has a frequency of about 250 hertz. What is set by this particular voltage source here? You see that. And now output is here, you see, at the label net out. So we click here, and we see that in the blue we have got the exact response. So the circuit passes this signal with a frequency 250 hertz satisfactorily, and it doesn't attenuate any signal. So it means it offers a gain of almost 1, because we see that the gain is constant and we have this signal. What about we change the frequency to, let's say, 700 hertz? So we'll see how the response looks like, and we click run again. And now we've seen that the gain starts dropping. It's not the maximum input, but we still have this signal getting filtered. So input is green and the output is blue. Furthermore, we go to 1000. So that's the maximum frequency or cutoff frequency of the circuit. Click OK. And we see now, if we zoom in, the input is 1.1 volt or 100 millivolt peak, and the output is about 70 millivolts. So you see now in the frequency response, it is 0.707 volts. So that's the response we are getting. So it's about minus 3 dB less than the original signal. Or in terms of voltage, the input is 100 millivolt and the output is 70 millivolt. So that's the limit. If we now increase the frequency, let's say you have 1200 or 1500, so on. So signal will keep dropping, the output signal, and we will be facing the attenuation. You see now the signal is about 65 and so on. So we don't really have the signal, proper signal filtering. So let's say it is about, I apply a signal of 5 kilohertz. So for that to have a proper result, let's reduce the time. It's about, let's say, 10 millisecond. Let's see how it responds. So yeah, you can see now the output signal is substantially dropped. So this is how this RC filter works. We'll see more.